In this lecture, we're going to finish up Chapter 24, covering the last couple sections on electric potential. Alright, so we're going to calculate the electric field from the potential. Now, previously we were finding the potential due to some electric field. Well, we want to do the opposite now. We want to try to find the electric field from the potential. So let's suppose that a positive test charge, Q0, moves through a displacement from one equipotential surface to the adjacent equipotential surface. The work the electric field does on the test charge during the move is going to be given by negative Q dV, which is what we've seen before. In the picture here, you can see kind of the situation. We're going from equipotential surfaces, and our distance in between them we're just going to call ds, because it's going to be a very small incremental distance. All right, the electric field is shown there, as well as our point in charge. All right, so the work by the electric field may also be written as the scalar product, right? Because work is F dot D. All right, so if we have our force, which is just Q0 times the electric field, and multiply that by our ds element, which is our distance away, we get the Q0 times the electric field cosine theta ds, right, because it's a dot product. All right. Therefore, we can say that this work is going to be equal to that, which is just the two definitions of work that we just found. And solving this for E, because we're trying to find the electric field, we're just going to say E cosine theta is equal to minus dV over ds, because everything else cancels out. The Q0s cancel out, and this is what you're left with. All right, so why this cosine theta? Well, the cosine theta is giving us the component of E in the direction of ds, right, because of the dot product. So we want to say that, so our equation then is just going to be the electric field in the direction that we're going, which is what we're concerned about, is equal to the partial derivative of the potential divided by the ds, the partial derivative of s. All right, so this symbol here is just partial derivative, in case you guys haven't seen it before. And we're really just going to do basic partial derivatives here. All it really means is all we're really worried about is one specific variable. So for instance, in the next line here, if we're trying to find the electric field in the x direction, we can then just take the partial derivative due to dx. Again, in the y direction it's the same thing, and in the z direction it's the same thing. So it really just depends on what direction we're going in and what piece of the electric field that we're trying to find. We'll do some examples so this makes a little more sense. All right, so therefore the component E in any direction is just going to be given as the negative of the rate at which the electric potential changes with distance in that direction, right? Because this is just going to be, since derivative is just a rate. Okay. All right, so let's go ahead and do an example. All right, the electric field at any point on the central axis of a uniformly charged disk is given by this equation, right? We found that in the previous lecture. So starting with this expression, derive an expression for the electric field at any point on the axis of the disk. All right, so we want to find the electric field as a function of distance z along the axis, right? Because this z here, if you remember, if we have our disk, this z is going to be coming up in that direction. All right, so we want to find the electric field along that line there from the center of the disk. So for any value of z, the direction of E must be along the axis because the disk has circular symmetry. Thus, we want to find Ez of the total electric field in the direction of z. So this component is the negative of the rate at which the electric potential changes with a distance z. All right. So thus, we start with our equation, which is given above. All right, so this is the surface charge density divided by 2 epsilon naught. And then we have the square root of z squared plus r squared minus z, which is outside of the square root. Okay. Now, to find the electric field, we just use our equation for the electric field in the z direction, which we just found on the previous slide, which was negative partial derivative dv over dz. All right. Fill in the rest, so we have negative surface charge density divided by 2 epsilon naught, and then we're just taking the derivative of z squared plus r squared minus z. Alright, so we can call this the full derivative because there's no other variables in the equation. Alright, we're just worried about the z, and that's all that we have here. Alright, so when we take this derivative, we need to take the derivative of this term and then subtract it from the derivative of this term. Well, the derivative of this, so if we say that this is z squared plus r squared to the 1/2, the derivative of that with respect to z is going to be 1/2. Oops. It's going to be 1/2 times the inside, which is just z squared plus r squared to the negative 1/2. And then multiplied by the derivative of the inside, which is just 2z. All right, so because of you have a half there and a 2 there, the z's, or the 1/2s, are just going to cancel. So our derivative is just z over z squared plus r squared square root. So the square root of z squared plus r squared. Right, so that was the derivative of the first term, and the derivative of the second term is just the derivative of the z, which will just be 1. All right, so if we write our answer then, the electric field is going to be sigma over 2 epsilon naught times 1 minus z times the square root of z squared plus r squared. Now, all I did was I took this negative sign here and I distributed through. And when I did that, this negative 1, which came from here, became positive, and this, which was positive, became negative, right? I just distributed the negative through. Okay. So, the electric potential energy of a system of point charges is going to be the next section. Alright, so the electric potential of a system of fixed point charges is equal to the work that must be done by an external agent to assemble the system. So bringing each charge in from an infinite distance separately. Okay, so the figure shows that 2 point charges Q1 and Q2 separated by a distance r. When we bring Q1 in from infinity and put it in place, we don't do any work because there's no electrostatic forces that are going to be acting on Q1. All right, so Q1 just by itself, if I wanted to pull a charge in from infinity and place it somewhere, there's not going to be any work required, all right, because there's no other forces acting on Q1. However, when we bring in the next charge, when we bring in Q2 in from infinity and put it in place, we must do work because Q1 is going to exert a force on Q2 during this move. Right? So if you place Q1 there, if you place Q1 there, and you then bring Q2 close to it, Q1 is going to have a force on Q2. All right, so we need to account for that. All right, so the work done is just Q2 times V, which is the electric potential that has to be set up by Q1 at the point where we put Q2, right? So Q1 has some electric potential at this point here, and that's what we need to consider. All right, so our potential is just 1 over 4 pi epsilon naught Q1 over R, which is going to be, again, the potential by Q1. And our potential energy is just equal to, our potential energy is just equal to the work, which is Q2 times V, right, which is our potential. All right, so all we end up with is K times Q1, Q2 over R. All right, so let's do an example problem with that as well. All right, so the figure shows that 3-point charges held in fixed positions by forces that are not shown. What is the electric potential energy U of this system of charges? Assume that the distance between them is 12 centimeters. All right, now it lists what the charges are. The energy is associated with each pair of electrons. Okay, so let's mentally build this system that's shown in the figure. Starting with one of the point charges, let's just say Q1. So again, if I put Q1 in place, I pull it in from infinity, it's going to require no work to get there. All right, so if we take this charge, pull it in from infinity, just put it there, no work done. So we don't have to worry about that. But then we bring in another one, let's say Q2 in from infinity, and place it in there. So from the previous equations, with D substituted in for R, the substitution the potential energy of 1 and 2 associated with the pair of point charges is given by this. So it's just the potential energy is Q1 times, K times Q1, Q2 over D, which is what we found in the previous slide. All right. Well, then we bring in the last charge in from infinity, and we put it in place. Now, the work that we must do in the last step is equal to the sum of the work we must do to bring 3 near Q1, and the work that we must do to bring 3 near Q2. All right, so we really just add this all together. All right, so let's see what this looks like. So really, our potential energy is going to be equal to the potential from bringing 2 close to 1 plus the potential of bringing 3 close to 1 plus the potential of bringing 3 close to 2. All right, so just add these all together. You have 1 over 4 pi epsilon naught, which is K, times Q1, Q2 over the distance, plus, Q1, Q3 over the distance, plus Q2, Q3, again, over the same distance. So the denominator is all the same, so this simplifies pretty easily. All right, so if we say this is, again, 1 over, 4 pi epsilon naught, and we go ahead and plug in all of our values for Q. Well, Q1 is just positive Q, Q2 is negative 4Q, this is divided by distance, plus Q1 again is just positive Q, Q3 is given as 2Q divided by the distance, and then again Q2 is negative 4Q, and Q3 is 2Q divided by the distance. Again, the denominator is the same. This all simplifies, so really just adding all the numerators together, you have negative 4Q squared here, 2Q squared here, and negative 8Q squared here. So our final potential is then just negative 10Q squared divided by 4 pi epsilon naught times D. If I wanted to get a value for this, we can just plug in our values. So we have K, which is 8.99 times 10 to the 9th Newton meter squared over Coulomb squared, times 10 times our charge, which is 150 times 10 to the 9th coulombs squared, all divided by our distance, which is just 12 centimeters or 0.12 meters. This gets us a value of negative 1.7 times 10 to the negative 2 joules, or that's also equal to negative 17 millijoules. All right, so this was the potential energy required to make this system of particles. All right, let's do another example. So in this one, we're going to talk about the conservation of mechanical energy with electric potential energy. So an alpha particle, 2 protons and 2 neutrons, move into a stationary gold atom, which has 79 protons and 118 neutrons. So again, an alpha particle is just basically the nucleus of a helium atom, right? Because 2 protons means helium. So really it's just the nucleus. So it passes through the electron region that surrounds the gold nucleus like a shell, and it's headed directly toward the nucleus. All right, so if you can see this alpha particle, let's say this is the gold nucleus here, you had electrons out here, so it's passing through the electron cloud and getting close to the nucleus. The alpha particle slows until it momentarily stops its center at a radial distance of r is equal to 9.23 femtometers from the nuclear center. And femtometer is times 10 to the negative 15. Right? So r is 9.23 times 10 to the negative 15 meters. All right, then it moves back along its incoming path. Because the gold nucleus is much more massive than the alpha particle, we can assume that the gold nucleus does not move. What was the kinetic energy, K, of the alpha particle when it was initially far, hence external to the gold atom? Assume that only the force acting between the alpha particle and the gold nucleus is the electrostatic Coulomb force. In reality, it's not, but let's assume so. All right. So an alpha particle, again, is traveling. It shows you that. All right, so talking about the reasoning here. When the alpha particle is outside of the atom, outside of the electric cloud, the system's initial electric potential energy is 0 because the atom has an equal number of electrons and protons. All right? So it has a negative charge and positive charge. They balance out. It's going to be neutral. So the electric potential then is 0. This produces a net electric field of 0 as well. Now, however, once the alpha particle passes through the electron region surrounding the nucleus on its way to the nucleus, the electric field due to the electrons goes to 0, right? Because we can kind of think of this as a closed spherical shell of uniform negative charge. Kind of think of it as a conductor. You have this shell of negative charge. When you're inside the shell, the electric field from the shell is going to be 0. So such a cell produces an electric field that's 0 in the space that it encloses. The alpha particle still experiences the electric field of the protons in the nucleus, though. So you still have some electric field, but it's only from the nucleus, the positive nucleus. And that produces a repulsive force on the protons within the alpha particle. Now, as the incoming alpha particle is slowed by this repulsive force, its kinetic energy is transferred to electric potential energy of the system. So you go from a particle that's going really fast into the nucleus, all of that energy turns into potential energy, right? Because it's slowing down. Well, the transfer is complete when the alpha particle momentarily stops, and then the kinetic energy, or the final kinetic energy, is then 0. All right, so getting to the calculations. The principle of conservation of mechanical energy tells us that if we add our kinetic energy, or kinetic and potential, initially, it must equal the kinetic and potential after, or whatever our second condition is. All right, so our first condition will be when our alpha particle is outside of the nucleus, out of the atom, and then the second condition is when it stops, when it's really close, when the alpha particle is really close to the nucleus of the gold atom. All right, so we know two values, that the initial potential energy is going to be 0, and that the final kinetic energy is going to be 0. We also know that the potential energy, UF, at the stopping point is given by the right side of the equation 24-43, which is the equation that we saw for earlier of potential. So that is this equation here, 1 over 4 pi epsilon naught Q1 Q2 over R. All right, so that's what our potential is. Okay, so the right side is given with this, so we know that Q1 is going to be 2e and Q2 is going to be 79e, which is just the number of protons, and e is our elementary charge. We know what our radius is. Thus, we can write the equation. So this equation is just going to simplify to So this equation is just going to be the kinetic energy initial is going to equal to our final potential energy. All right. So we can just take this and we'll plug in our previous equation, and this is just going to be, so our kinetic energy initial, which is what we're trying to find, is 1 over 4 pi epsilon naught times 2e, which is the charge, 79 e. Oops. Just want to make a quick correction. This is u up here. This is the potential energy, u, divided by 9.23 times 10 to the negative 15, right? Because that's our radius. Okay, so this is just going to equal our kinetic energy will then equal 3.94 times 10 to the negative 12 joules. Oops, joules. If I wanted to convert that to electron volts, you would just divide by E. So this in electron volts is going to be 24.6 mega eV, which is times 10 to the 6th. All right, so here's our kinetic energy that we found in joules. It might be interesting to see, well, how fast was it going? We have some bit of kinetic energy. It's actually a pretty low number, but I wonder how fast it's actually going. So let's see. If I were to try to find the velocity of the alpha particle, you could simply say, well, our kinetic energy is 1/2 mv squared. And our kinetic energy was 3.9. Actually, let's just do it this way. Let's go ahead and solve for velocity because that's what we're trying to find. So if I rearrange this equation for velocity, you just get the square root of 2k over m. Plugging everything into here now, you get 2 times k, which is we found as 3.94 times 10 to the negative 12 joules. And we divide that by the mass. Well, the mass is going to be the mass of the alpha particle. And the alpha particle is 2 protons and 2 neutrons, which means there's 4 particles. And the mass of each particle is roughly 1.67 times 10 to the negative 24. That's in kilograms. Okay. So we find that the velocity is about 1 times 10 to the 6th meters a second, which is about 1 million meters a second, which is, I would say, pretty fast. All right, a couple more things to finish up. So let's talk about the potential of charges in an isolated conductor. So an excess charge placed on an isolated conductor is going to distribute itself on the surface of that conductor so that all points of the conductor, whether on the surface or inside, come to the same potential. Right, so you get this equipotential surface. This is true even if the conductor has an internal cavity and even if that cavity contains a net charge. So we know that our equation for electric potential is given there. Since for all points E is equal to 0 within the conductor, it follows directly that Vf must be equal to Vi. Right? Our initial potential must be equal to the final potential. Right? Because if this is 0 inside of the conductor, that means this whole term is 0. And that you just have Vf minus Vi. So rearranging that, you just get Vf is equal to Vi, which means the potential must stay the same anywhere inside the conductor. All right, so the plots here are showing that so the first one is showing the potential by the radius. So we can see the potential stays the same if the radius is 1. The potential is going to stay the same throughout the entire conductor. And the electric field we've seen before is going to be 0 inside of the conductor. And then, of course, it's going to taper off from there as you get further and further away. All right. So spark discharge from a charged conductor. And some of this might sound a little bit familiar because we sort of saw some of this ionization of the air when we were working with the Van der Graaf generator. So on non-spherical conductors, a surface charge does not distribute itself uniformly over the surface of that conductor, meaning at sharp points or edges, the surface charge density, and thus the external electric field, may reach very high values. Now, the air around such sharp points or edges may become ionized, producing the corona discharge that golfers and mountaineers see, and again, that corona discharge is what we saw with the Van der Graaf generator. So golfers and mountaineers see on the tips of bushes, golf clubs, rocks, hammers, when thunderstorms threaten. So such corona discharges are often the precursors of lightning strikes. In such circumstances, it's wise to enclose yourself in a cavity inside a conducting shell where the electric field is guaranteed to be zero. A car is a great example, unless it's a convertible or made with some kind of plastic body. It's actually almost ideal. All right. An isolated conductor in an isolated electric field. All right, so an uncharged conductor is suspended in an external electric field. The free electrons in the conductor distribute themselves on the surface as shown, so as to reduce the net electric field inside the conductor to be zero. Because as a conductor, the electric field inside must be zero. And it makes the net field at the surface perpendicular to the surface. Alright, so if an isolated conductor is placed in an external electric field, all points of the conductor still come to a single potential regardless of whether the conductor has any excess charge. Alright, so whether there's excess charge on it or not, it in itself is an equipotential surface. So the free conduction of electrons distribute themselves on the surface in such a way that the electric field they produce at interior points must cancel the external electric field that would otherwise be there. Furthermore, the electron distribution causes the net electric field at all points on the surface to be perpendicular to the surface. So if the conductor in the figure could be somehow removed and leaving the surface charges frozen in place, the internal and external electric field would remain absolutely unchanged. Alright, so basically you have these charges redistributing themselves so that inside of the conductor, the electric field is zero. Alright, that's it for this lecture. We'll catch you next time.